Right now, beneath the Alps, near the city of Geneva, Switzerland, there is a tunnel. And machinery inside that tunnel sends beams of energy in a vast circle.
Studying quantum mechanics has challenged and reshaped our understanding of the physical world. It's been dubbed as the most successful theory in science because of its accuracy in predicting particle behavior at the quantum level. However, its basic principles and interpretations are still the subject of heated debate and investigation. It's pretty difficult not to talk about CERN in this context. For those unfamiliar, CERN is a European company that researches the fundamental structure of the universe. And today, we'll be looking at one of its recent announcements. Physicists at CERN announced the discovery of 3 new exotic particles as they search for more information about the mysterious forces that bind subatomic particles together. The discovery of the particles, a new type of pentaquark, and the first tetraquark pair occurred on a historic day at CERN at the Geneva lab, which also restarted its Large Hadron Collider after a 3-year pause with the machine's most powerful beam of energy yet. Following painstaking maintenance and repairs, the restart provides another opportunity for a global network of scientists to search for the strong force that holds atom nuclei together. The strong force, along with the electromagnetic force, gravity, and the weak force, governs the decay of particles. The Higgs boson's anniversary was marked last year, and for those not familiar, this is a milestone that helped to solidify the so-called Standard Model, which accounts for the fundamentals of particle physics. The Higgs boson, named after the Nobel Prize-winning physicist who discovered it, is thought to have existed at the creation of the universe, just moments after the Big Bang, about 13.7 billion years ago. However, physicists continue to question the Higgs boson and look beyond the Standard Model. It's the most complete one we have, but it needs to explain where gravity comes from, what exactly dark matter is, or why there is so much more matter in the universe than antimatter. Its massive underground ring, stretching beneath 27 kilometers of countryside across the Swiss-French border, is aided by a series of superconducting magnets to propel subatomic particles to near light speed to smash them together as powerfully as possible. Slamming protons together at high energy in particle accelerators like this can produce tiny fragments of the universe that are not normally visible. The LHC's detectors have a better chance of detecting the smallest and most exotic particles when the energy level is high, as in a car crash. CERN's engineers have turned the beams of protons up to unprecedented energies, producing collision energies of about 13.6 trillion electron volts, up from 13 in the previous run, along with new magnets that must be kept at a cool -271.3 degrees Celsius, just colder than outer space. 1 trillion electron volts is approximately the energy of a flying mosquito. Well, for a subatomic particle, that's a lot of energy. CERN claims that the beams around the ring will eventually carry the same amount of energy as a train traveling at 150 kilometers per hour. The particle beams will also be denser, increasing the likelihood of a collision and the possibility of producing Higgs bosons, discovering new particles, and possibly discovering new physics. One of the most sought-after items is the axion, a hypothetical particle that does not generate, absorb, or reflect light. It's one of the leading candidates for the composition of dark matter, the enigmatic substance physicists believe accounts for 85% of all matter in the universe. The discovery of the first tetraquark pair and the new pentaquark and torrents of data gathered during previous LHC research will help explain how subatomic particles form. Hadrons are particles that make up the mass of most ordinary matter, such as protons and neutrons and atom nuclei, and more exotic hadrons are made up of 2 to 3 elemental particles called quarks. However, physicists began theorizing 6 decades ago that, in rare cases, these combinations can form 4-quark and 5-quark particles. These so-called tetraquarks and pentaquarks have only recently been observed by the LHC and some other experiments. The new pentaquark is the first to be discovered to contain an unusual quark. CERN physicist Niels Tuning compared the current era of discovery to that of the 1950s when a particle zoo of hadrons was unearthed, ushering in the quark model of conventional hadrons in the 1960s. The new findings, in particular, will aid theorists in developing a unified model of exotic hadrons and better understanding of conventional hadrons. While several theories describe exotic hadrons as balls of tightly bound quarks, others envision them as pairs of standard hadrons, loosely bound in a molecule-like structure. However, a bit more research is needed to determine whether either or both theories are correct. According to CERN researchers, the statistical significance of the pentaquark discovery is 15 standard deviations, which is significantly higher than the threshold of 5 standard deviations set by the physics community for claiming the observation of a particle. These new tetraquarks are the first pair of tetraquarks to be discovered, and their statistical significance ranges between 6.5 and 8 standard deviations. ATLAS, the LHC's largest experiment, employs over 5,000 scientists from over 40 countries. Other new CERN experiments probing the nature of the universe will concentrate on collisions of high-energy ions to better understand the plasma that existed only in the very first microsecond after the Big Bang. Some of these include probing the insides of protons, studying cosmic rays, and looking for the hypothetical magnetic monopole, an isolated magnet with only one magnetic pole. Other detectors will aid researchers in their investigation of extremely light and weakly interacting particles such as neutrinos and dark matter. CERN marked the start of Run 3, the third time the LHC has collided since its inception in 2008, surpassing the previous largest particle accelerator, the Tevatron in Fermilab, Illinois. These runs will continue until the machines are upgraded again in 2026, and each participating country contributes to the multi-billion-euro project. The Biden administration initially allocated only $40 million for future LHC upgrades in the fiscal year 2022, far less than the approximately $90 million that was required. And according to the American Institute of Physics, the Department of Energy later diverted an additional $25 million from various physics projects, including a set of upgrades at Fermilab. During this run, the researchers behind the LHC's 2 main experiments collided bunches of about 100 billion protons at a rate of 40 million collisions per second, each of which produced around 60 smashes, each of which produced hundreds of particles. Tuning explained that the more analysis they run, the more exotic hadrons we find. But are these experiments risky? Well, for various reasons, people have speculated over the years that CERN experiments could endanger the public. Fortunately, such concerns are unfounded. According to UK Research and Innovation, the N in CERN stands for nuclear. This can naturally cause some bit of tension, but it has nothing to do with the reactions that occur within nuclear weapons, which involve the exchange of protons and neutrons within nuclei. CERN's research is conducted at an even lower level, in the constituents of protons and neutrons themselves. It's sometimes called high-energy physics, but the energies are only high on a subatomic scale. And according to the LHC Safety Assessment Group's safety report, particles inside the LHC typically have the energy of a mosquito, which is really low but very high when we're talking about subparticles. People have also expressed concern that the LHC will create a mini black hole, but even if this occurs, which is unlikely, it will be so small and unstable that it will vanish in a fraction of a second. This is not the only big experiment from CERN. It has a record of other impressive experiments. Antimatter frequently appears as one half of a particle-antiparticle pair inside CERN's high-energy accelerators. However, in normal events, antiparticles are annihilated in collisions with ordinary particles. You'll need more than an accelerator to create antimatter that can be studied in depth. This is where CERN's one-of-a-kind antimatter factory comes into play. It takes antiparticles produced by the proton synchrotron and then slows them down to manageable speeds in the antiproton decelerator, effectively the inverse of a particle accelerator. The resulting anti-atoms can then be studied using a variety of instruments. A smaller instrument called MODAL, or Monopole and Exotics Detector at the LHC, shares the same underground cavern as LHCb. While most CERN experiments are specifically designed to study known particles, this one intends to discover previously unknown particles that exist outside the current standard model. A monopole, for example, is a magnetized particle with only a north pole and no south pole, or vice versa. Such particles have long been speculated about, but never observed. MODAL's mission is to detect any monopoles that may form due to collisions within the LHC. It could also detect certain stable massive particles predicted by theories other than the standard model. MODAL's discovery of any of these particles could help to answer fundamental questions about the existence of different dimensions and the nature of dark matter. At this rate, we should expect more mind-blowing experiments from CERN.